Hello and welcome. In this video, we'll close out our lecture set on simple linear regression by discussing how we can assess statistical assumptions of simple linear regression using R. So to start out, two things. First, we're going to be pulling the data set and just the simple linear regression model. So not very much we're going to start with today because we're not going to be building a lot of this by hand. We will, but we're going to not have to build core components. We're going to be able to use some stuff pretty easily from just the linear model itself, the linear model object in R. The second thing to note for the assumptions is we're going to focus on the graphical assumptions that we talked about in the lectures. We're not going to talk about all the statistical assumptions, and these are by no means the only ways to assess assumptions or the only concepts to do. So treat this as a relatively minimal, straightforward introduction into checking out assumptions. I hope it's helpful for you, and I think it is very useful, but this is not by any means comprehensive. So just lawyering up there, a little bit of caveat, and with that, we'll jump right in. So we're going to be doing a few of these by hand, and by hand, I just mean we're going to be building these from the ground up. Now, for a lot of the by hand stuff in this course, quite frankly, I just don't do it that way. You know, I don't build a t-test or an ANOVA or a regression by going back to the sum of the squared errors and manually calculating that. With that said, for this by hand stuff, I sometimes do build these by hand. That is, and again, by hand, take that in quotes, you'll see that we're only going to have a couple of lines and then we're going to have the plot built. So it's not as much work as like building an inferential test statistic or something, or confidence interval. With that said, the reason I do that a little bit more with this stuff is because some of the stuff for the built-in graphics, some of the built-in stuff just does different things than I tend to use for interpretation. So remember, with graphics, the whole thing is they're a little bit subjective. So doing something that can help you interpret this better is useful. And that's one of the reasons I like building some of these pieces myself. And again, I think you'll see that this isn't actually too bad to build. So again, for the y-hat, and I see I didn't actually run my stuff to start. Now that I have my y-hat values. Again, we can just do predict SLR mod, and that gets all my y-hat values. One other cool thing, so I could calculate E by finding y minus y-hat. That works here, but I can also calculate E by just doing resid SLR mod, and this pulls all of the residuals from the model. And again, these are just y minus those y hats that we just calculated. These are all the same. Don't have y. So my y variable here is profit. So I can use profit. And so I can see E, the resid from the model, is just the same as the observed y's minus my predicted y's. That's all I'm looking at here. And recall that to create my graphic, essentially what I do is I do my residuals on the y-axis and my y-hats on the x-axis. Now, I said that in the lecture videos, and that is true, but one thing I want to do is I want to introduce the concept of a standardized error. All I'm going to do with the errors is I'm going to subtract the mean and divide by the standard deviation. Now, that sounds kind of weird, and in R, we can do that really quickly by using the scale command. This is the same thing as taking, say, E minus the mean of E, wrapping that all in parentheses, and dividing by the standard deviation of E. So this is what that command does, scale. And what this ultimately does is it turns this into a scale where the new variable, standardized E, has a mean of 0 and a standard deviation of 1. Now, this doesn't actually change the distribution, and I'll show you two plots, one with the regular E and one with the standardized E. They're not going to look that different. In fact, in this case, the regular E's are so close to their standardized versions that even the axes aren't going to look that different. But the reason that we sometimes use the standardized values for the residuals instead of the regular raw values for the residuals is that with the standardized value of the residuals, we can mentally compare them to our normal distribution. If you remember back to your previous course or the review, the empirical rule with the normal distribution said roughly 95% of the data fall within 2 standard deviations, and roughly 99% of the data fall within 3 standard deviations of the mean. And so what we do essentially when we look at the standardized residuals is we can keep an eye on just how far outside of that range are our errors falling. All right, so to put this plot together, I'm going to do x equals y hat. Again, y hat values are on the x-axis, and my y-axis values are my errors. So again, I'm going to make 2 plots, one with E and one with that standardized E. If you look in the bottom right, when I run this, you can see it change in 3, 2, 1. So that update, that was just a little tiny update that made. And the big thing I want you to see, actually the scale of the y-axis when you do this with a different data set can change drastically. But what I want you to see is that when I go back and forth between the images, the actual data points don't move at all. All that moves is the scale of our y-axis. And again, that's a useful thing in an applied setting, because essentially I can say anything that's outside of, say, plus or minus 2 in a standardized scale might be something that I want to investigate, depending on how many observations are out there and how far out they are. So sometimes you'll see them with the standardized error instead of the regular error. That's just fine. Does it really matter? No. Again, with our residual plots, we're looking for patterns. Using the standardized version lets you see an additional potential pattern, which is I'm having really big errors, things that should be pretty unlikely, but I'm having a lot of them. So that might be helpful sometimes, but doesn't have to be. AB line, you can just do the top one for the purposes of this course. AB line H equals 0, LTY equals dotted. What this is going to do is add a line. Remember, we used AB line before with our regression line. H equals 0 is new. That says make a horizontal line at the value 0, and LTY dotted says make this a dotted line. So this adds a nice dotted line at 0. This should be the middle of our graph. And so we can kind of look at all the things that we look at with our residual plot. We look at the spread. We look at, is the spread relatively consistent across it? Are there any nonlinear patterns, etc.? With this plot, this is really sparse data. You might say, oh, it's less variable, or oh, it's more variable, or oh, it looks like it's going down. But remember, with this sparse of data, could it just be random chance that both of these values are below the line as opposed to above it? Yeah, it could very well be random chance. And so because of that, you want to be hesitant a little bit about what kinds of decisions you're making, especially with sparse data. I mentioned this, this is one of the things with graphics. With sparse data, it's tough to identify patterns, but note that that's true with the statistical methods too. With sparse data, it's tough to identify statistical violations of normality, and it's tough to really believe that, especially when you just don't have that many data points. All right, so let's jump into our next plot, the QQ plot. So that was our residual plot. Let's do our QQ plot. So for our QQ plot, I really like using the standardized errors, and it's because with the standardized errors, that puts the errors on the same scale as the standardized normal distribution, the z-scores, which is what the QQ plot is essentially based on. So when these things are on the same scale, then we can use a line at 0, 1 to look at the diagonal line that these should fall in. If we don't put them on the same scale, this works. And again, just like with the graphic, when I switch back and forth between the standardized error and the not standardized error, the dots stay the same. When I do the Q norm stuff, the dots is going to stay the same too. The QQ plot stuff, the dots are going to stay the same too. What we're doing isn't changing the pattern of the dots. What we're doing is changing the scale of the axis. So for this case, again, I like doing the scale of the axis to be based on the standardized error as opposed to the regular errors. It just is a little bit more flexible for this type of thing. The command to create the plot is QQ norm. And so when I do that, I have my QQ plot nice and drawn up here. Now note that this QQ norm command does not by default provide a diagonal line. I can add that on. There's a couple of different ways I can do that. But for me, when I'm using standardized errors, I like to use the AB line. I'll put the y-intercept at 0, and I'll put the slope at 1, and I really like this. I'll again make the line type dotted. That just makes it a little bit prettier, I think, but that's completely aesthetic. And then I can look at this graph. Again, not very much data, maybe like this weird lazy S shape a little bit, but that top dot doesn't really conform to that. So essentially not really enough information. Remember, this is an assumption check. The null hypothesis is my assumption's fine. So you have to provide convincing evidence to convince me that something's not fine. Could there be something wrong here? Yeah, there could, there couldn't, but I'm not convinced. So I'm going to stick with my null hypothesis that everything's fine. All right, well, I guess our last thing is the built-in functions. And again, I hope I've convinced you that actually building these by hand is not bad. It's not as bad as the by hand sections on a lot of things we did. Actually, I do the Y hat here just to show you that this E is correct, but you could completely skip that Y hat step. Just make your E, stick it into a, oh, I guess not. I guess you need the Y hat step for X. So never mind. You pull these, you stick them into a plot, you do the AB line, and you're done. For the built-in function, if you want to be even slightly more efficient, though have less control over whether or not your middle line is dotted or not, you would do the plot command and you would feed in your regression model, SLR mod. Now this is going to give you a bunch of different statistical diagnostics plots, some of which you might like, some of which you don't. To just pull these two, you can use the which command and give it a vector of two numbers, 1 and 2. You could have it provide as many plots as you want, but we just want the first two. That'll be the residual plot and QQ plot. When I run this, Control Enter, this is going to ask me up here to go up, click into here, and hit Enter or Return to see the next plot. So I go up, I click Enter, and that's going to show me my residual plot. Note that for the purposes of helping to identify when the pattern is nonlinear, this residual plot provides a moving average line so that I can see when things are jumping up and down. With just a few data points, this isn't particularly useful, but when I have a lot of data points, this might be useful to identify or help identify nonlinear patterns. Again, I want to be convinced, and I'm only concerned if the violation is moderate or larger. Small violations or deviations, even if systematic, is not a particular concern to me, though I guess the linearity one, maybe that's not quite as true, because I do want to make sure all variables are accounted for in the model, and violations of linearity might indicate there's a missing variable. Going up to the top right, clicking in again and hitting Enter one more time pulls up the second plot, and that looks very, very, very similar to the plot that we just put together ourselves. In this case, again, we have our residuals, we have our quantiles. You note that these are the standardized residuals, the one that we made up here, these standardized residuals, and we see this plot with the same dotted line. I will say that the built-in plot does have a slightly different dotted line than the one that we make. If you can tell, this dot here, this second to the last dot, is slightly above the line in the one made by R, and it's slightly below the line in the one that we made. So these are slightly different graphics. They do slightly different things. In R, it uses the 25th and 75th percentiles to create the values to draw the line, and in ours, we use the theoretical values. So it doesn't really matter. It's just a line. We want all the dots to be on it as close as they can, you know. But I think these can both be helpful. And again, this is what R provides by default. So again, this is one of the reasons I actually like for the QQ plot. I rarely use the built-in plots for the QQ plot. I typically make my own, and it's because I can define that diagonal line. If I want to use the quantiles, I can, or I can just make it the typical line starting at 0 and going up by 1, again, reflecting that theoretical relationship. Alrighty, ladies and gentlemen, well, this has been quite the ride. This ends our lecture discussion on simple linear regression. So yeah, closing out. I hope this was useful for you. I do think that this is the start of a huge step in an analytics journey, because this is the foundation for our next concept, multiple linear regression, which literally combines almost everything that we've talked about in the course, everything except for the chi-square testing. Outside of that, everything, the ANOVA, the t-tests, the regression, the correlation, all of that is combined in a multiple linear regression. We can do all of them at the same time, which is kind of crazy. So that's where things get really, really cool, really, really creative. We can do curves, we can do categorical variables, we can do continuous variables, we can do it all. And this essentially serves as the foundation. You're going to feel a lot of that is very similar to this. And so I appreciate you sticking with me. This was a long lecture set, a lot of lectures, the R videos. Actually, the R videos I felt went pretty quick, but maybe you felt the R videos went on a while too. But yeah, this was a lot. So in any case, thank you so much for sticking with me, not just through this video, but through the whole lecture set. I appreciate it, and I will look forward to catching you in the next video.